Acids and bases. Acids have a sour taste. Vinegar owes its taste to acetic acid, and citric fruits contain citric acid. They react with certain metals to produce hydrogen gas, and they react with carbonates and bicarbonates to produce carbon dioxide gas. Bases have a bitter taste. They feel slippery, and many soaps contain bases. A Bronsted acid is a proton donor, and a Bronsted base is a proton acceptor. Here we have ammonia reacting with water to form ammonium ion and hydroxide ion. If we look at the forward reaction, we see that the water donates a proton to the ammonia, making it an acid and the ammonia a base. If we look at the reverse reaction, we see that the ammonium ion NH4+ donates a proton to the hydroxide, making the ammonium ion an acid and the hydroxide ion the base. This is referred to as a conjugate acid and a conjugate base. The acid-base properties of water. Water, amazingly, autoionizes into hydrogen ion and hydroxide ion. It's an equilibrium, shown here schematically. And here we have two water molecules in equilibrium with the hydronium ion H3O+ plus hydroxide ion. The hydronium ion H3O+ is simply an H+ aqueous ion. The water molecule on the left acts as an acid, and the hydroxide ion is the conjugate base. The second water molecule is a base, and the conjugate acid is the hydronium ion. The ion product of water is written as an equilibrium constant, the hydrogen ion concentration in moles per liter times the hydroxide ion concentration over the concentration of water. The concentration of water is constant, especially compared to hydrogen ion and hydroxide ion, which are very small numbers. We then write Kw, which is the product of the hydrogen ion concentration and the hydroxide ion concentration. It's referred to as the ion product constant. It's the product of the molar concentrations of H+ and hydroxide at a particular temperature. At 25 degrees, this Kw is equal to 1 times 10 to the negative 14th. If the hydrogen ion concentration equals the hydroxide ion concentration, the solution is neutral. If the hydrogen ion concentration exceeds the hydroxide ion concentration, it's acidic. And if the hydrogen ion concentration is less than the hydroxide ion concentration, then the solution is basic. pH is an easy way to measure acidity. It's defined as minus the log of the hydrogen ion concentration. That's the base 10 log. The solution is neutral if the hydrogen ion concentration equals the hydroxide ion concentration. Since at 25 degrees the hydrogen ion concentration is 1 times 10 to the minus 7, then the pH is 7. For an acidic solution, the pH is going to be less than 7. And for a basic solution, the pH is going to be greater than 7. As the pH increases, the hydrogen ion concentration decreases. Here is pH table of some common fluids. Notice that stomach juices are 1 to 2 in value of pH. Saliva 6.4, 6.9, blood about 7.3, and household ammonia, which is very basic, is 11.5. There's some other important relationships we should know. The pOH is minus the log of the hydroxide ion concentration. The ion product, remember, is 1 times 10 to the negative 14th. If we take logs of both sides, minus the log of the hydrogen ion concentration, minus the log of the hydroxide ion concentration is going to be equal to 14. Therefore, the pH plus pOH equals 14. If you know one, you can calculate the other. Remember that strong electrolytes are 100% dissociated. Weak electrolytes are not completely dissociated. Acetic acid is about 3% dissociated into acetate and hydrogen ion. Strong acids are strong electrolytes. HCl, HNO3, HClO4, and H2SO4 are examples of this. Weak acids are weak electrolytes. Here are two examples. HF is a weak acid. HNO2 is also a weak acid, as is bisulfate ion HSO4-. Water is also a weak acid. Strong bases are strong electrolytes. Examples of these are sodium hydroxide and potassium hydroxide and barium hydroxide. Notice that barium hydroxide, when dissolved, gives you 2 hydroxide ions. Weak bases are also weak electrolytes. Fluoride ion, nitrous ion are examples of weak electrolytes. Conjugate acid-base pairs. The conjugate base of a strong acid has no measurable strength. Hydronium ion is the strongest acid that can exist in aqueous solution, and hydroxide ion is the strongest base that can exist in aqueous solution. Look at this diagram of a strong acid. Before ionization and then at equilibrium, notice that the HCl is completely dissociated into H+ and Cl-. Contrast that with a weak acid, HF. Before ionization and at equilibrium, the amount of HF is not much different than before ionization. A small amount dissociates into H+ and F-. This contrasts a weak acid with a strong acid.